So this is now lesson 8A, third part, and I will now discuss to you the lesson on gradients. Let's have the definition of gradient. It says here the gradient vector can be interpreted as the direction and rate of fastest increase. If the gradient of a function is non-zero at point P, the direction of the gradient is the direction in which the function increases most quickly from point P, and the magnitude of the gradient is the rate of increase in that direction. Further, the gradient is the zero vector at a point if and only if it is a stationary point where the derivative vanishes. The gradient thus plays a fundamental role in optimization theory, where it is used to maximize a function by gradient ascent. Mathematically, the gradient of a function in two or three variables, so where we have here the definition, if f is a function of x and y, then the gradient of f is defined by, we have here the symbol read as del f, meaning the function in two variables xy is equal to the partial derivative of the given function evaluated at xy with respect to x times I plus the partial derivative of the given function f evaluated at xy with respect to y times j. Then we have here the gradient of a function of three variables. It says here, if f is a function of x, y, and z, then the gradient of f is defined by del f of x, y, z is equal to partial derivative of the given function evaluated at x, y, z with respect to x times I plus the partial derivative of the given function evaluated at x, y, z with respect to y times j plus the partial derivative of the given function evaluated at x, y, z with respect to z times k. Let us work on this example. So it says here, find del w or gradient w if we have w is equal to ln of the square root of x squared plus y squared plus z squared. So let's recall the formula. So this is a function that involves three variables. So we now have the del f of xyz is equal to f sub x evaluated at xyz times I plus f sub y evaluated at xyz times j plus f sub z evaluated at xyz times k. So let's start with finding the partial derivative of the given function, which is w with respect to x. And we have evaluated at x, y, z. So with that, this is our function w. So let's recall the formula for ln u also. So the derivative of ln u with respect to a variable, say x. So it is the derivative of u with respect to x all over u. So in this case, so since we have here a radical ln of the square root of x squared plus y squared plus z squared, we can also write this as ln of the quantity x squared plus y squared plus z squared raised to 1/2, and applying the property of natural logarithm, and that property is ln number power is equal to power ln number. So therefore, this function w can also be rewritten as w equals 1/2 ln of the quantity x squared plus y squared plus z squared. So let's now get the partial w with respect to x. So applying this formula that we have, so we have the constant 1/2, so it's 1/2 multiplied by, we have the differential or derivative of the given function u, which is x squared plus y squared plus z squared with respect to x. So y and z will be considered as constant, so the derivative of x squared is 2x all over u. U here is quantity x squared plus y squared plus z squared. And we can now simplify by canceling 2. So this will give us x all over. We can have now x squared plus y squared plus z squared. So that will also be your f sub x in the formula here. Then let's now get the w sub y because our function is w. So let's have our symbol w sub y. So finding now the partial derivative of your function w with respect to y. So taking into consideration rather that x and z will be considered as constants. So we have here the function. So copy your constant 1/2. Get the derivative of ln u. So let's get first the derivative of x squared plus y squared plus z squared with respect to y now. So x squared and z squared will be 0 because they are both constants. So we have here now 2y all over u. U is the quantity x squared plus y squared plus z squared. So we can cancel 2 so that the result is y all over x squared plus y squared plus z squared. Then finally, let's get the partial derivative of the given function w with respect to z. So this is our function. So this time x and y will be considered as constants. So copy your constant 1/2, then taking out the derivative of ln u. So x squared is 0 because it's a constant. Same with y squared, it's also 0 because it's also a constant. Then z squared derivative is 2z all over the quantity x squared plus y squared plus z squared. Then simplifying, let's cancel 2. So this will give us z all over x squared plus y squared plus z squared. So to find out del w or gradient of the function w with the symbol inverted delta, so we'll just collect the partial derivative of the given function, then multiplied by the ijk notation. So we have now x all over quantity, or rather x squared plus y squared plus z squared times I, then plus y over x squared plus y squared plus z squared times j. So we have that, the first and the second term. Then the third term will be the third partial derivative of the, or rather the partial derivative of the function w with respect to z, which is z all over x squared plus y squared plus z squared times k. So this is the answer for this problem number 1. Verifying my answer on this slide. So as we can see, we have here the same answer.